Okay, so here's a problem. It's a simple support at B. You can see I've got a pin at A and a roller at B. That is a roller support. And we've got a triangular varying distributed load with a maximum value of 3 kips per foot on the right side. And we want to find the internal shear force and bending moment at point C. So, like our previous problems, I think it's instructive to kind of imagine the structure cut at C, because that's where we want to find the forces, and then examine which side you want to look at, the left side or the right side. For just discussion purposes, let's examine what we'd have to do if we chose the right side. Well, for starters, we need to find the reaction at B. Okay, that's reasonable. If I chose the left side, I also have to find reactions at A, so that's kind of a wash. Those are equal. But now examine the two load scenarios. If you look at the right-hand side, what do you have? A trapezoidal load. And the left-hand side is simply a triangle. Now you can do the right-hand side. It's not hard. It just is a little more work. And I know the area of a trapezoid, but I don't remember off the top of my head the centroid of a trapezoid. So typically what we do at this point is we would break it up into two forces, right? There would be a force for the rectangular portion through its centroid and a force for the triangular portion. So just with that as a background, I think you can see that a single resultant force, which is all I need on the left-hand side, seems to be the easier way to go. So with that, I'm going to now say, okay, I'm going to work the left side. So once I make that choice, I need to find my reactions at A. So let's do that first. So I'll come over here first and redraw the free body diagram for this structure. So at A, I will assume that I have a Y and an X reaction, and then at B, well, it's a roller. I'll also have a vertical. Now, I need to find these reactions for the structure. If you look over the whole structure, the structure is a triangular distributed load. So what would be the concentrated equivalent of that? Well, the area of a triangle. 1/2 base times height. The base looks like to be 18. The height is 3. So that should be 9 times 3, which is 27. Does that seem reasonable? And it will occur 1/3 of the length from the big end. So it looks like I have a 27 kip force, and this will be located 6 feet from B or 12 feet from A. Is that okay? Yeah.
Why is it not just 12 times 3?
12. Because I'm doing the entire structure. So the structure has a length of 6 plus 12. Right, we're not just doing this part of it, right?
Okay.
We're doing the whole structure to find the reactions. Now I want to find the reactions at A, so what do? Where do I sum moment? I'd sum moments at B. So using right-hand rule as my sign convention for my moments, I'm going to sum the moments at B and make sure my structure is in equilibrium. Now about B, my concentrated equivalent force creates what kind of moment about B? Positive or negative? Positive. So the force, 27 kips, and the distance from B to the force, 6 feet. Then the other force I have that creates moment is my reaction at Y. What kind of moment does that create about B? Negative. So I'll have AY, and the distance from B to A, 18 feet. So that tells me that AY is equal to 9? No. Is that right? 9?
Yeah.
So 9 kips. And that's all I need from that free body. I've now got my reaction. So now I'm going to come down here and do a free body diagram of this section from A to C. We've already talked about why I chose the left-hand side. So I'm going to draw this a little bit larger, make it a little easier to see. So there's the structure. It's 6 feet long. We just found the reaction AY, so I'll place that on the structure. And then we have the distributed triangular load on the structure. And one thing we need to find out right now, I didn't know, is what is the intensity of the load right here at 6 feet? Well, I know that all the way down here at the end, which is at 18 feet, it has a value of 3. So similar triangle should tell me that at 6 feet it should have a value of 1/3 of that, so it should be 1. You guys see that? So that should be 1 kip per foot is the loading right there. You guys see that? The other way you can do it is you can find the slope of the line, rise over run. So the rise is 3, the run is 18, so that'd be a slope of what? 1/6. So every foot you move to the right, the intensity goes up a 6, so you go 6 feet. 6/6 or 1. A lot of different ways to get that. So now with that done, I can now calculate the concentrated equivalent of just this section on the left. Again, it's 1/2 base times height, so it'll be 1/2 base 6 times height 1. That gives me a value of 3 kips. And what's the distance to the centroid from the left side? 1/3 the distance, or 2 feet. Everybody see that? So now I'm going to actually find my internal forces. So this is where I'm going to come in now and assume positive shear at C and positive bending moment at C. So these are my sign conventions for shear force and bending moment. We've talked about those before. Now if you're working this problem on the exam, this is half the problem. As far as I'm concerned, maybe even 60% of the problem, because this is where you diagnose the problem, understand what's required, and do the basic transformation to create a free body diagram. I think that's more than half the problem. At this point, it's just apply equilibrium. You've done that a few times before, so you should be pretty skilled at that. So applying equilibrium, making sure this object is in equilibrium in 2 dimensions, what do? Usually whenever we cut a section, we sum moments. So with right-hand rule as my sign convention, I'm going to sum moments at the cut I just made and make sure this structure is in equilibrium. Now why is summing moments at the cut important? Well, the shear force passes through the cut, it creates no moment. So I should get one equation and one unknown. That unknown is the moment. So let's do that. So with right-hand rule now as my sign convention, this moment is positive, the moment at C. About the cut, the 3 kip force is positive or negative? Moment. Positive. So that has a force of 3 kips and a moment arm of 2 feet. And then my reaction at AY, which I forgot to write in, I know that's 9 kips. That reaction force creates what kind of moment about the cut? C. It creates negative, so that would be 9 kips, and its moment arm is 6. So solving for the moment at C, it looks like you get 48. Yeah, you guys get 48? And it positive, right? That'll be kip feet. Now, since I got a positive value, that means, yes, it does have positive bending moment at C. Does it make sense that you'd have positive moment at C? Well, I say yes, that it does. In fact, under this loading, you would probably get a deflected shape that looks something like that. Maybe not, obviously, to scale, but you can see that just about every point on the structure, you're seeing that positive curvature upwards, which is kind of happy, smiling, positive. So that matches the fact that we got a positive sign here. So how do we find the shear force? Well, it's in the y direction, so we should sum forces in the y direction. Now, I'm going to sum forces in the y direction and assume that up is positive. So that means this shear force, when I sum forces, is what? Negative. It's acting down. Also acting down is my 3 kip concentrated equivalent force, and then what's acting up? The 9 kip force. So it looks like the shear at C is equal to 6 kips. And that's that. Any questions about this? Pretty straightforward problem after you make I think a wise choice to work the left side. Would we have gotten the same results if we'd have worked the right side? Yes. It would have just been a little more effort to do. So I think it's always best to try to take a little time at the beginning of the problem and think it through. You usually have 2 choices. Think it through and say mentally, what will I have to do to work the left side? What will I have to do to work the right side? I can do both, but the right side's I'm going to have to make a couple extra calculations, so why do it? There's no advantage. Okay, any other questions about that?